element of the mapping class group of a surface is pseudo-Anosov. So the obvious questions here is, what does pseudo-Anosov mean, and who cares? So for this, we have to go back to the prehistoric times of around 1979 or something, when Bill Thurston has showed that all the surface automorphisms up to isotopic can be divided into 3 classes. Those that are periodic, that's pretty obvious what that means. Those that are reducible, which means that you can take the surface and decompose it along a bunch of curves so that the automorphism permutes those pieces, and on those pieces it acts in some mysterious way which we don't care about, because then we can do it recursively. And then all the rest. So this seems like a pretty stupid classification, but in fact, of course, the point was that Thurston had a lot more to say about the 3rd class, which is the most interesting. Now you say, why would that be? And the answer is that if you take a surface and you glue it, so you take a surface coordinate interval and identify the ends by that automorphism, then the resulting object is hyperbolic if and only if the mapping is pseudo-Anosov. And of course, hyperbolic 3 manifolds, as we all know by now, are very important for mankind in all kinds of useful applications. Okay. But anyway, there's a philosophy that Thurston had, which was that almost all 3 manifolds are hyperbolic. So the best known example of this is the Dehn-Surgery theorem, where you can take your favorite manifold, drill out a torus, and screw around a bit. And for most of the ways you could screw around, you get a hyperbolic manifold. So here, again, if you take almost any, the argument is, surface automorphism, then the resulting object should be hyperbolic. That's the motivation. Now, whether Thurston himself had asked this question in those exact words, I'm not sure. It certainly had been popularized by Benson-Farb, and Kapovich, in his great wisdom, said, well, this should be easy, he said. Just look at the symplectic representation of the mapping class group. Now, what is a symplectic representation, you may ask? Well, every automorphism of a surface acts on its first homology. Not only that, it preserves the intersection pairing. If 2 curves intersect once, then if you perform an automorphism, their images also intersect once. So, and if you do it the right way, then you'll see that this is a symplectic action, and you have a surjection from the mapping class group onto the symplectic group sp2gz. And now I should say, before I go on to the next slide, there's a problem with what I'm going to say. With respect to mapping class group, with what I'm going to say. I'll come back to maybe address this problem later. And the problem is this, that in fact you can write the mapping class group as a semi-direct product of the interesting piece, which is a Torelli subgroup, which is a subgroup of all those things that acts trivially on homology, and the symplectic group. Now, I have nothing against the symplectic group, but it's not that interesting as groups go compared to the Torelli group anyway, which is a very mysterious, deep, dark object. But of course, the good thing about the symplectic group is that our methods actually work there. They'll actually work in greater generality, but I'll talk about that a little later. Anyway, with that mysterious aside, on the next slide, so Casson has these conditions which appear in the book by Casson and Bleiler, which are, I guess, notes of lectures of Casson taken by Bleiler, which I guess this was like in also early 80s. I think at that point that was the only way Casson would ever write it down, is by having somebody else do it. So, so these are, take your transformation, take its image in the symplectic group, and see if the following 3 conditions held. First of all, the characteristic polynomial of the image is irreducible. Secondly, it is not cyclotomic. Thirdly, it is not of the form g of x to the k for some non-trivial k. So notice that this is kind of like the Thurston classification in an algebraic setting, right? Because not cyclotomic basically means that the thing is not periodic. And not of the form g of x to the k basically corresponds to it not being reducible. And, well, irreducible means irreducible. So it's kind of algebraic analogs. But so if these conditions hold, then the automorphism is pseudo-Nosov. So, OK.
Is that if and only?
No. So that's part of the problem, is that there are things in the Torelli group, in fact, most of the things in the Torelli group, which are pseudo-Nosov, and of course satisfy none of these conditions because the heuristic polynomial is x minus 1 to the to g.
So I know what Anosov means. What is pseudo-Anosov?
Well, pseudo-Anosov is almost like Anosov. So so notice, so the Anosov means that, right, there's the expanding contracting foliations. So it's the same for pseudo-Anosov. You can have two foliations, and one of them is expanded by this as you flow along this, or you iterate this map, and the other one gets contracted.
Yes.
So it's like, well, that's the difference.
What's different?
Because you cannot have a foliation of the whole surface. There are going to be gaps. Yeah. So it's what you mean by foliation is a little bit different. It's a singular foliation.
Okay.
But otherwise, it's the same. Right. OK. So the point is that if you want to prove a genericity result for pseudo-Nosovness, if this were almost always true in the symplectic group, we'd be done. Well, we would be done at least for the whole mapping class group. OK. So what do we do? So are the Casson conditions generic? So that's what we want to check. So now we forget about the mapping class group entirely, and we are in the comfortable world of linear groups over the integers even. So what does generic mean exactly? What is a generic element of SP2GZ? Well, I'm sure you can come up with a million conditions, all of which are completely different. But here we're kind of in the combinatorial group theoretic setting. So we think in terms of generators and, well, we don't think about relations in this. So we take a generating set, and we look at the combinatorial ball in the group of radius r. And we'll look at all the words, all the elements which have words of length at most, whose minimal way of writing it is of length at most r. So there's some number of words, which is finite. And we ask, so there's some number of elements, probably a lot. And we ask if the condition holds for almost all of them as r becomes large. That's a natural definition. Unfortunately, it is a little difficult to work with, because these groups, even though they're finitely generated and finitely presented, the presentations don't really have very nice properties. And so one easily gets confused.
Is it even independent of the generating set?
That's a good question. So it is not obvious that it's independent of the generating set. And in fact, to come up with it, but the question is, can you come up with a definition which is independent of a generating set? And of course, well, there's a naive way of doing it and saying, well, if that's true for all generating sets, well, right? So that's basically what we do. And actually, I'll give a slightly different thing, which is of that kind.
In hindsight, it's independent, but not.
Yeah. So,
they're strong. It doesn't depend on what generating set you choose.
and well, in fact, I'll say a little bit more of this in a moment. So interpretation 2 is we say, well, you know, these relations, they're really too much trouble to work with. Forget about them. Just look at all the words of length n. Maybe they could be written as a word of length 3. We don't care. Just look at all the words of length n, and do the same kind of definition. So the difference is that there's cancellation that we're not keeping track of. Now, it should be true, not only should the generating sets be irrelevant here, but in fact it should be true that something that's generic in one sense should be generic in the other sense. I have no way of knowing how to prove this. Well, no, I might have some way of knowing, but I don't know what that way is. But so in fact, we'll give an interpretation which is stronger than the second one, and sometimes includes the first one. So take a graph, which is undirected. That's very important. What I'm going to say does not work if you assume the graph is directed. Peron-Frobenius means it has its adjacency matrix has a unique eigenvalue of maximum modulus. So it's the condition that always comes up in these kind of questions. And graph, the word graph is actually not correct, because in a sense that it could be multigraph. You can have self-loops in this graph. That's OK. And then what you do is you could have two edges between. That's fine. It doesn't. It won't come up in this application, but everything I'm going to say works fine for that case. So what we do is we put group elements, or actually generating set elements. So gamma is a generating set. We put elements of the generating set on the vertices of G, and then we walk along the graph, and whenever we see an element, we multiply it to what we've seen before. So that means that if you have all the walks of length n, that translates into a set of elements, possibly with multiplicity, in fact, almost certainly, on the group. And
the steps of the walk are given by the elements of this generating set gamma, is that right?
the steps of the walk are given by the edges of the graph.
Oh, okay, okay.
But the word we get is given by the elements of the generating set that we see. So we say that something is generic if it's generic for any choice of G satisfying these conditions. So it's much stronger than doing it for any one G. Now, my interpretation 1, or 2 actually, where we just take all the words without care for what they're canceling, corresponds to a certain choice of G. So for free group on two generators, this is the graph. Every vertex is connected to every other vertex, and in fact, to every vertex, including itself. So the walks will just correspond to all words, and then we can cancel them. You say, well, that's a very stupid-looking graph, or stupid model, but we can easily make only reduced words by changing your graph to this. Just do not connect the element to its own inverse. That will give us the usual words in the free group. So in fact, so this is where the dependence on the generating set comes in. So what is this graph, really? You can think of it as an automaton that generates words in the group. So if the group, and you have an automaton and it's undirected, so if the group that we're working with had a biautomatic structure, then the interpretation 1, which is we look at all the words in a ball, will fall into this framework. So it means that there's a language, a regular language, that recognizes the shortest paths from point to point. And we want this language to be, furthermore, in such a way that the automaton can be taken to be undirected. That's biautomatic, and it's a well-known open problem about mapping class groups, whether they admit such a structure. It is known, due to work of Lee Mosher, that they are automatic. So if we don't insist on the undirectedness, then yes, there's an automaton that recognizes it. And there has been a claimed result of Ursula Hammerstad that they're biautomatic, but I don't know that anybody's actually read it yet. It's been claimed on and off for many years, so there's a certain amount of skepticism. But notice that biautomaticity or automaticity depends on the generating set. So if this result is true, then there is a generating set for which we can say this ball thing. But it certainly is not clear for every generating set. All right. So now what? So as it happened, so when Kapovich asked me this question, I started thinking about products of random matrices and oscillated theorems, and because I thought the hard part was keeping it away from being cyclotomic, but that's not the hard part. And then I said, well, almost everything is irreducible. Surely this must be known. Well, surprise. So I had been looking on the distribution of elements. Look at the free group and look at the abelianization. Look at the large ball, combinatorial ball in the free group, and ask how the elements are distributed in homology classes, or so in the abelianizations. You have a projection map, you have a fiber. Look how the size of the fibers are distributed.
Sorry, how do you get homology classes out of the free group?
Just abelianize. Every element has an abelianization.
In the group homology, then, in the homology of the group.
If you want, yeah. But you don't have to mention homology at all. Just look at the size of the fibers in that ball over the abelianization. The reason I was looking at this question is because Peter had many years ago had this work with Phillips on distributions of geodesics and homology classes. And they had this observation, which I guess Peter had connected to the Chebyshev bias somehow, is that even though things were equidistributed, nevertheless the differences between the number of null homologous geodesics and some fixed homology class were always positive. So why should this be true? And my view was that there must be some kind of a unimodality going on. So indeed, and I said, well, surfaces are too complicated. That actually requires knowing some dynamics, which I don't. So I'll just look at the simple combinatorial model, which is the free group. So free group is about as simple a group as you want, and yet surface groups are almost free. So hey, so it worked. And you can prove a central limit theorem. And then if you look at compact groups or finite groups and look at the same model, you have walks on the graph, and you can show that under a condition, which is, I'll tell you what it is that all the generators don't lie in the same. So there's no representation that maps them all to the same element, which is kind of a stupid condition.
What does the central limit theorem say? I don't understand the data there.
So look at the large ball. Well, actually, look at all the walks of length n on the graph,
Yes.
which is the automaton for the free group, if you want, but any other group satisfying the conditions. Look at all the walks of length n and look at their images in the abelianization. They define the probability distribution.
In the abelianization.
Yeah.
Okay.
They define the probability distribution if you just divide by the total number.
Mm-hmm.
And the probability distribution looks like a Gaussian. That's all. You can actually prove a lot more results of this kind. You can prove local limit theorems, and in fact, there has been a lot of work on this since. So Sharp extended to surface groups, I think, and also proved a local limit theorem, even though it was implicit in the original paper. And then Danny Caligari and Koji Fujiwara have put it into completely general context with quasimorphisms and combable groups and combings, and they're basically everything you can shake a stick at has a central limit theorem. So life is good. But anyway, here I only care about the finite group result and the equidistribution statement. And so we had a nail, we've made a hammer, and so now we're working on the symplectic group. And what we do is for every prime, we show that the Casson condition, or whatever the conditions we need, hold for a constant fraction of each element, of all the elements. And then we use the standard algebraic groups machinery to lift to the whole thing. Now, in fact, again, miraculously, other small hammers were found, or large hammers were found along the way. So Nick Chavdarov, who was a student of Katz, in his thesis, he has the exact right statement one needs for characteristic polynomials of matrices in finite symplectic groups, which was actually not due to him. He attributes to Armand Borel. I guess he came here and asked Borel, and Borel told him. But there are, I think, other combinatorial proofs of this fact. But you have enough equidistribution to get the right result. And then you can use the same methods for SL and Z. And the statement actually is that the generic matrix has the full Galois group as the full symmetric group as a Galois group. So for the symplectic group, so for every ergodic graph and every generating set, yeah, so we're counting the number, and so as the words get longer, this property starts holding almost always. So the Galois group is the full Galois group. Now the Galois group for matrices in the symplectic group is not the symmetric group, and it's because the characteristic polynomial of a symplectic matrix is reciprocal. So in other words, because coefficients are the same read left to right or right to left. In fact, it is surprisingly recent result. I mean, I couldn't find an early proof of this fact that every reciprocal polynomial is the characteristic polynomial of a symplectic matrix. Should have been known to Sylvester or somebody, but
Who did that?
well, the earliest proof I could find is due to a person named Kirby, but not the Kirby you think about, a different Kirby from England. And it's actually, in my paper, I just copy the proof because it's a little hard to find. But again, it should be essentially a triviality, but hey, somebody had to say it, and he did. It's a very short proof. So anyway, so the Galois group statement implies all the Casson conditions in one swell loop. Also, what about the SL and Z case? So for the surfaces, we only care about the symplectic group. What about SLN? Well, it turns out mankind, in its great wisdom, has also studied automorphisms of free groups. And again, an automorphism of free group acts on the abelianization. So you have, you can ask similar questions, and the analog of pseudo-Anosov is what used to be known as irreducible with irreducible powers, and because people are lazy, they called it IWIP, which is a horribly ugly word, and therefore saner minds insisted on calling it strongly reducible. So, but again, the condition is that essentially the action homology has no invariant factors, but that should be true for the automorphism and all of its powers. So it's a natural condition, which was first invented, I think, by Bistvin and Fein. So you can show this, and again, the powers one gets from the Galois group. Irreducibility of the polynomial is not enough, obviously, for this. And then, if you think longer about the SL and Z case, there's a joint result with Ilya Kapovich, which actually appeared in a paper of mine, is that what I said before, why is pseudo-Anosov interesting, is because when you look at the mapping torus, that's hyperbolic. Well, if you look at sort of the mapping torus of a generic group automorphism, that's word hyperbolic. That's the result. So hyperbolicity is really pervasive in all its forms. So the results are effective, but in the sense that you can get explicit bounds on the. So what I didn't say is that the proportion of words which are reducible among the words of length n is exponentially small as a function of n. Now, of course, exponentially small is a function of n. The exponent depends on the generating set, and it depends on the graph you take. That goes sort of without saying, but I'll say it anyway. But the point is, one cannot prove anything without assuming that the generating set is symmetric. Now, you could say, well, that's probably because I'm too stupid to do the general case. But in fact, I'm not sure that's true, because there are many results like this, of this sort, and you always wind up assuming symmetry. And my conjecture for why that's true is like this result of, I think it's Markov. Let's look it up. Is that in linear groups, for any n bigger than 2, if you have a bunch of elements and you ask, do they generate the group as a semigroup? That question is undecidable. For SL3, it's, I think, equivalent to the post-correspondence problem or something. So, of course, for a symmetric generating set, everything is good, because then a semigroup is the group, since you have inverses.
So what does it mean for a given set?
For a given set, well, presumably there are some sets for which you can decide, but there are some sets for which you cannot. You can find a set of generators of elements for which you cannot decide whether it generates a group or not. Now, notice that it's very bizarre, because, for example, it will generate any finite quotient. Because notice, if it didn't, you could decide. And also, because of the theorem several slides back, if it satisfies some mild technical condition, it's a generating set of the finite group, and therefore it will become equidistributed. So it will even be equidistributed in every finite quotient. But you cannot decide whether it generates the whole group. Oh, annoying.
But is it better if you, in the symmetric case, can you decide if some set of elements generate as a group,
Well, but what does it mean that it generates a semigroup? It means you cannot take inverses. But if the matrix is the generating is symmetric, you've already taken inverses.
He's saying it generates whatever it generates. That's what makes it hard.
Instead of, you can replace semigroup by group, and then if you assume that it generates the group, then you're.
Oh yes, but if you don't assume it generates the group, is it decidable or not?
Good question. Is it? I assume. It's a good question.
I think that there's something like that that would be able to be measured, yes. Because these possible subgroups there would be quite limited.
Group can be quite thin.
Yeah, it can be quite thin, I agree.
Yeah, I don't know the answer. I'm assuming that it is decidable, but I might be assuming wrongly.
Sorry, are these given set of matrices, is this a finite set or possibly?
Finite set.
And so is there such a finite set known?
Well, how do you know it? I mean, does it?
No, he's asking you,
Can you produce such finite set?
is the explicit set, does the logic proof give an explicit set?
I'm assuming the answer is yes. I don't know the proof, but I assume the answer is yes. And I'm assuming the set probably can be taken to be fairly small. In fact, I wouldn't be surprised if the set could be taken to be 2 matrices.
I think those kind of statements, one proves that there is no algorithm which if one inputs a set, then out of it comes yes or no.
So there are stronger and weaker forms of the statement, right? One is that, and the other one is, like for groups, right? The indecidability of the word problem.
That's meaning that you give yourself element and generators and relay, and then you ask, but you want for an algorithm working for all system of generator and relay.
But the question is, for groups, right? The word problem is undecidable. But is it true that there exists an actual set of generators and relations for which you just don't know? And never will know.
No, so that's this kind of thing one could not prove.
Because I thought in the original Novikov thing there was something like that. But
This one reduces always to some hunting problem, so one needs always a class.
so some diagonal argument, you think? Yeah. Good question. I don't know. But anyway, so under the assumption of symmetry, the results are effective. You can get explicit bounds on the size of the decay. But of course, the question is how close that is to the truth. So one can ask what the truth actually is to know that whether what we're proving, so this is a bit of an experimental aside, actually has anything to do with reality. And actually, yesterday before giving this talk, I said, well, I should have some pictures. And so for SLNZ, there is a natural generating set, which is the one, I think if you ask somebody what is the generating set for SLNZ, they'll either say they don't know, or they'll tell you that it's the transvections. What are transvections? These are elementary row operations. You take a matrix, which is diagonal, and then you have a single of diagonal 1. Those are transvections. Their inverses are just like that, except there's a single diagonal -1. Because transvection corresponds to adding one row to another row, so the inverse is subtracting one row from another row. So the first generating set is all transvections, which is a very large generating set. It'll have O of n squared elements. And the second one can be found in the paper of Hua and Reiner from 1948, which has 2 generators. So SLNZ can be generated by 2 matrices. One of them is a transvection. I mean, in their case, it's the one that has adds the first row to the second row, or no, the second row to the first row. And the second one is, I don't know how to describe it. It has 1s below the main diagonal, just on the big subdiagonal, and -1 to the n minus 1 in the top right-hand corner, thereby assuring that it's actually in SLNZ. So these 2 matrices generate, and here's some pictures. So for transvections, for SL2Z, what are transvections for SL2Z? These are the 2 parabolics, right? And notice, it looks like there are 2 graphs superimposed. So what is this a graph of? It's a fraction of the polynomials of the matrices, which can be written as words of length n. So the x-axis is the length of the word, and the y-axis is the fraction of those words which have reducible characteristic polynomials, which is something we've proved should go to 0. Luckily for us, this visibly does go to 0. But notice it looks like 2 curves. I mean, there are 2 things that are amazing about this. One is that if you plot this curve logarithmically, it looks like a straight line. So it's really a pure exponential, which is a little surprising, even for such small values of n. I think the value of n here goes up. Why are the 2 graphs? Yes. Even an odd gives you what looks like 2 different curves. So one of these is even values of the word length, and another one is odd values of the word length, which is kind of surprising that they look so different. So, OK. SL3Z, suddenly it looks like 1 curve, though if you look at numbers carefully, there's still 2 curves, but they're very close to one another. SL4Z looks even more steep and looks even more exponential. Actually, I did the experiment for SL5. The graph becomes steeper and steeper, so it becomes less and less interesting. And for Hua and Reiner, again, very similar. So here the generating set for SL2, right? It's the parabolic and the rotation by pi over 2. So again, even though it's quite different generating set, you still have this huge even-odd dichotomy, which is very strange. And again, the curves look very smooth and exponentially decaying. There seem to be no higher order terms. Oops. For 3, looks similar. For 4, you get, again, what looks like 2 curves, but it really depends on the parity. So what do you make of this? Well, I'm not sure what to make of it. I mean, it would be, you can compute, if you do a linear regression on the logs of these numbers, you get, and you do statistics, you see that the error bars are very narrow. The exponential decay coefficient is very tight. It's plus or minus 5% from this very small amount of data. So that tells you something. I'm not quite sure what. And that's true for different generating sets. So one could do the same experiment for the symplectic group, but since I just did it yesterday, I didn't have time. For symplectic group, there are again two generating sets I know of. The transvections, which are a little bit different in this case, or Hua and Reiner in the same paper find a generating set of cardinality 4. Not 2, but 4. All right. So what other notions of genericity are there? Well, there's the Archimedean height. So you look at all the matrices in SL and Z where the elements are smaller than n in absolute value, and there, to use these methods, initially I was trying to use Duke, Rudnick, and Sarnak's paper, but it doesn't have quite enough information because you want to have a result for different congruence subgroups, but independent of P. You want to have bounds which don't depend on P. And this can be found in Nevo and Sarnak's paper, which at the time I was writing was a preprint, but now may have appeared. Has it appeared? Or is well, it's written. Okay. That's always a plus. Now one question about this, which is this experiment that I showed you just on the previous slides. Question, how would you do that experiment for the Archimedean height? In other words, how do you generate a random matrix in SL and Z with bounded entries uniformly? And I know of no way of doing it. Because notice, of course, you can write down random integer matrices and see the determinant is 1, but that might take you a long time. So I know of nothing resembling an efficient algorithm to do this. So this is a very interesting algorithmic problem, I think, but that might require a lot of number theoretic understanding. But so this experiment I could not do for the Archimedean height. I think for SL2Z one can do it, but above that, yeah.
Just sample a uniform one and check if the determinant is 0, is 1.
Is what?
You can just sample a random matrix and check if it's in SL.
But very few with the determinant 1.
So it's not.
So
it's not.
it's not feasible. Yeah, I mean, clearly generating a random matrix with all entries less than 17 is easy. But the percentage of them that's going to have determinant 1 is rather small. I think even for n equals 2, I think it's the number of matrices, I think it's quadratic. And
Elena Fuchs has done something like this for orthogonal groups, right? U and cat. Exactly what they do. But they prune the tree very carefully and mix the Archimedean with the word. We can discuss it.
right. I mean,
Works quite well.
right. On the other hand, the orthogonal case is easier. So, but that's already very interesting. Okay. So another question, which is in a different direction, is what happens for smaller groups. So what I didn't tell you, the original question about the mapping class group, when I proved the result, I wrote about it to Benson Farb, who's been popularizing the question. And then that day at the University of Chicago, there were two talks, mine and this guy Joseph Marr, who is now at CUNY, who proved the result for mapping class groups in complete generality. So for me, it was the whole mapping class group at the time. He could do it for any non-elementary subgroup of the mapping class group. What's non-elementary mean? Basically, not generated by a single element or something. So it was a really amazingly good result with one. And
particularly, you can prove it for Torelli.
he can prove it for Torelli, subgroups of Torelli, anything.
Now, what do you mean by non-elementary? C2 would not work.
Non-elementary, I think if you look at the action on the projective elimination space, something there has to be more than 2 limit points or something like that. That's the condition. So it's sort of an analog of the elementary for subgroups of SL2R. So
Is it easy to prove it for Torelli, for instance?
it is not easy. So
What I was asking is the non-elementary
yeah, you just find enough elements, and you'll see it. You just look at different. I mean, Torelli is generated by pairs of Dane twists. So if you look at one pair and another pair, they'll mix together. So yeah. So Hughes results are not effective. So, but they're still great results, and they're completely general, and they use completely different methods. They use the curve complex methods, really geometric group theory. Here I'm using essentially arithmetic methods. So, so this talk was immediately adjacent to mine, and that has really gotten my goat, because well, surely I should be able to extend this to be to a bigger class. And the observation, which I guess everybody here probably knows by now, is that so Matthews, Wasserstein, and Weisfeiler have this famous paper, which I guess was extended later by Weisfeiler in different directions, that if you have a Zariski dense subgroup, then almost all the projections mod P are onto, which means that the sieve methods, in effect, which was one using there, one can use without change here. One question to which I've never been able to find an answer, and maybe because there isn't one, is how effective is the almost all part? And I'm assuming the answer is not very.
I think the proofs of Larson and Pink offer some chance of that.
I mean, I actually, when I was writing the paper on this, I actually wrote to Wasserstein. Sadly, Weisfeiler fell off a mountain somewhere, and I don't know who Matthews is. But Wasserstein's answer was basically, I don't know, I don't care. So, which was a little puzzling, because that's the obvious question. On the other hand, there are results of
I'm a bit perplexed. You have to have linear groups, so you're going to take your Torelli, you have other representations in mind, which are going to be linear?
no, so no, but notice notice the original result is for the full mapping class group.
Yeah, but that you prove.
Yes, but you can actually, this way you can get much thinner subgroups of the mapping class group, because you can get much thinner subgroups of SP.
Oh, yeah, but suppose you want to recover.
Yeah, so this does not give you Torelli, but it gives you much smaller subgroups. And actually, there's a sort of a converse to this method Weisfeiler that Katz had mentioned. There's a German guy whose name escapes me. That if you're onto, not Pink, starts with a W. If you're onto like mod 5 or something, then you're Zariski dense.
This is all under simple connections.
Well, for those groups, I think it works. For Symplectic and SLNZ, it works, I'm pretty sure. So you can check easily. You just don't know how long it will take you, but you can check easily. So this does not work for Torelli group, because then the image is trivial. And a trivial group, sadly, is not Zariski dense. If it were, then we would all be much happier than we currently are. Now, in fact, for the mapping class group, Justin Malestein, who's a postdoc with me, and Juan Soto can extend my method to do it for Torelli. And the idea basically is, the germ of an idea is that if you look at the cover of a surface, then Torelli, final cover, double cover even, then the Torelli group acts non-trivially. So for double cover, there's the old homology and the new homology, and the non-Torelli, the mapping class group, acts on the old homology, but Torelli acts non-trivially on the new homology. And there's a long and, to me, completely incomprehensible paper of Lubotsky and Grunewald, where they use this fact.
So you're using those they are linear representations of the mapping class, which sort of.
Well, they use this observation to construct new representation of Torelli, right? You can get sort of virtually faithful in both directions. You have a finite index subgroup of Torelli, which is virtually onto the symplectic group. So you construct those representations. It's not clear what to do with them because, after all, you have to have an analog of Casson's conditions to check, which is not obvious. And but Malestein and Soto, they use look at a bunch of different lifts, and they kind of can find one that works, and then they use some analog of Casson to get this. And their method, as far as I know at the moment, works for finite indexes subgroups of Torelli. I'm guessing that if you apply this with this Zariski density idea somehow.
The theorem is the same.
Same, yeah.
Generically.
And again, it's effective. The point is it's effective. I mean, there's no point trying to recover Mar unless you can do that. So the other direction that, again, I've kind of touched on and other people have developed along is a kind of effective. So one thing about this Zariski dense thing is, in fact, you can prove the following result, that a generic, so generating a Zariski dense subgroup is a generic condition. So pick an element and pick a random, in my sense, element. Then those two together will generate a Zariski dense subgroup, generically. So in that sense, you kind of can leverage up this genericity a few times. So if you want the source of Zariski dense subgroups, knock yourself out. The other thing you can ask is sort of a generic version of Titz alternative. If you have two elements, you would expect that they would usually generate a free group. Because why shouldn't they, basically? And this is true. So there's a student of Emmanuel Briard called Richard Aoun, whose thesis is proving this for linear groups. And then Dennis Austin and Bob Gilman and Masnikov, I think, have this result for hyperbolic groups. The generic subgroups of hyperbolic groups are free. Well, when the Aoun thing, it's basically the same definition. You take two elements to take these walks on graphs. I mean, I'm not sure if he does quite in the same generality, but similar. And pick two elements at random. And then you check if it's the subgroup generated is Zariski dense, and or free, right? In his case, free. Yeah, I think for him it's probably the simplest case with a graph as a complete graph. But whatever he does should work the same. But yeah. So both freeness and Zariski density are generic properties. But anyway. So at this point, I should stop, I think, and if there are any questions.